This is the Interstellar Travel Energy Issues project from the Special Theory of Relativity Dynamics section. In the Interstellar Travel Kinematics Issues project, we looked at some of the fundamental difficulties in traveling to a relatively nearby star. Now in this project, we're going to look at the incredible amounts of energy needed to accelerate a macroscopic object to relativistic speeds. So, we have a fully fueled spaceship of mass m. So the mass m is the spaceship plus the fuel. And then after burning some of the fuel, the spaceship has a smaller mass. This is the useful mass of the spacecraft, the payload, which we will designate as F, little f, times capital M. Oops, that was supposed to go down here. And this would be the spaceship plus whatever it's carrying, except for the fuel. Then your job is to find an expression for the amount of fuel. I think they mean the mass of the fuel. So if this is the mass of the spaceship plus the fuel, and this is the mass of just the spaceship, then the mass of the fuel would be this minus this. You get to write that down on your own though. Okay, so then here for part A, step 1, you want to find the energy released by this conversion. Use what you learned in the nuclear physics section in order to answer this question here. And you're looking for the energy released. So you know that the rest energy is equal to mc squared, and because there's a small difference in the rest energy of what we start with initially and what we end with finally, that difference in the rest energy is going to be the energy that's released. Okay, and then in part 2, you're calculating the efficiency of the reaction, and for that efficiency we use a little epsilon. So that's the efficiency. You have to calculate that, and then for step 3 on the top of page 46, you're going to use your expression for the total amount of fuel on the spacecraft, so that's the first thing that you calculated, and the efficiency of the fusion reaction to write a symbolic expression for the total energy released by fusing all of the fuel. So you have the mass that you found on the previous page, and so it's going to be that mass times the efficiency, because you don't get all of the energy, you just get some fraction of the energy, times c squared. So this would be the mass times c squared, giving you the energy, but then since you don't get all of the energy, you have to multiply it by the efficiency. You're supposed to do this symbolically, so all you need to do here is sub in for the mass of the fuel what you have on the previous page. Okay, and then we're looking at the kinetic energy of the payload. The payload is F times the mass, which is what we have here. So that's the spaceship plus whatever it's carrying other than the fuel. And we know kinetic energy is equal to gamma minus 1 times the mass times c squared, and the mass that we would be using here is the mass of the payload, so the mass is F times capital M times c squared. And we're supposed to equate this kinetic energy with the total energy released, which is what we have up here. So this is equal to the energy from step 3, and then you are to solve for F. In the previous investigation, which was the Interstellar Travel Kinematic Issues project, you should have found that the cruising speed was 0.9992 C, or you should have had at least something close to that, in order to reach Vega in a little less than 3 years. Using the result from above, what fraction of the mass of that spaceship can be payload, and how much of the ship must be made up of fuel? So you're going to use this, which came from the previous project. You have to calculate gamma, which actually I guess you would have done in the previous project. So you could just use that. And then use your expression for F. From the previous step. And also, you're going to be plugging in numbers here, so you will also need the efficiency that you calculated on page 45. And they tell you here you should have found that 99.97% of the mass of your spaceship must be fuel, so your number that you get here should agree with that, and if it doesn't, you should have your instructor check to make sure that you are using the correct values for step 5. Okay, then on page 47, we're going to look at step 7. So, how much fuel is required for a complete round trip? And we're going to express our answer as a multiple of the payload mass. The payload mass is what you have left over after all of the fuel has been used. So you're going to Vega and you're coming back to Earth. When you get back to Earth, you should have a mass which is equal to the payload mass. So you don't need any fuel for cruising by Newton's first law. And so you only need the fuel for speeding up and for slowing down. You do need fuel for slowing down because you are changing your speed. So we have 4 different stages. We have speeding up from Earth initially, then slowing down when you approach Vega, then speeding up on the return journey when you're leaving Vega, and then slowing down when you get back to Earth again. And because I know the mass that I want to end up with, I'm going to begin with stage 4 and work my way backwards to stage 1. So stage 4 would be slowing down as you approach Earth. Stage 3 would be speeding up when you leave Vega. Stage 2 would be slowing down as you approach Vega. And stage 1 would be speeding up when you leave Earth. When we end up back on Earth, we are going to have a mass which is equal to the payload mass. I'm going to call this M sub P for the payload mass, and it told us express your answer as a multiple of the payload mass. And this is the mass of the ship, but in this column here we're going to do the mass of the ship plus any stored fuel. But we don't have any stored fuel when we make it back to the Earth. And then in this column here, we're going to put the fuel needed for this stage. And then back in step 6, we calculated the fuel to payload ratio, which I'm going to call R, but you should have a number for that from step 6. And so the fuel needed for this stage would be that ratio times however much mass you're trying to accelerate or decelerate. So you end up with this much mass, and you need this much fuel to slow down this mass. So then at the end of stage 3, the mass of the ship plus the stored fuel for stage 4 would be this plus this. So this plus this is going to give you this number here, and that would be R plus 1 times MP. And then you take this value, and to get the fuel needed for this stage, you multiply it by the ratio that we have here. So that's R times R plus 1 times the mass of the payload. And then to get this value here, you add this and this together, and that goes there. So that's all the mass that you have at the end of stage 3 plus the fuel that you need for stage 3, and that goes there. Okay, so you continue down the table like this, add this value, multiply this value by R to get what you have here, then add this and this together to get what you have here, then multiply it by R to get this value here, and your answer is going to be this plus this, and that's, actually that's not how much fuel is required. That would be the mass of the ship and the stored fuel. But you could take this and subtract from it the mass of the payload to get all the mass of the fuel, and think that should be equivalent to just adding up everything in this column here. You want it as a multiple of the payload mass, so the final step would just be to take the number that you have here and divide it by MP. Then on page 48, we are going to look at what would happen if you tried to collect fuel along the way. So you get to read through this part on your own. You're going to set the kinetic energy of the collected atoms equal to the energy that can be extracted from the atoms. So kinetic energy, remember, is equal to gamma minus 1 times the mass. So let's just say the mass of the collected atoms is equal to m. So that would be mc squared. And the energy that you can extract from the atoms is equal to the efficiency times the rest energy. So you set these two equal to each other and solve for V. And remember that gamma is equal to 1 over the square root of 1 minus V squared over C squared. So that's where the V comes from. Okay, and then for page 49, you're going to look at a ship which is powered by matter and antimatter, and combining the two in a controlled way. So here for step 1, we have, after combining the matter and antimatter, the photons traveling in a tight beam away from the stern of the ship. So for this engine, determine F, the payload fraction of the initial mass of the ship, to achieve a cruising speed V. Hint, this is what we want. The ship can essentially be considered to be a particle of mass m at rest that decays into a big flash of light, and a smaller particle, the payload, of a known mass Fm traveling at a known speed v, conserve both energy and momentum. Okay, so this is what we're going to do here. Initially, we have the ship at rest And a ship at rest would have a momentum of 0 because the velocity is 0. The mass of this total ship with the fuel is capital M, and since the ship is not moving, the total energy is just equal to capital M times c squared. So that's what we have before. Afterwards, we have two things. We have the payload moving this way, let's say, and we have the light, which if the payload's moving this way, the beam of light would be moving the opposite way. So, the mass of the light is 0. The mass of the payload is little f times capital M. So mass is not conserved, but energy is conserved. And we know that the energy of a beam of light is equal to its momentum. So we have E light here, and whatever that is, it would be equal to the momentum. And total energy is equal to gamma times the rest energy. I'm just going to call that E naught. So here, the mass is little f times capital M. So the total energy is gamma times the rest energy, which is the mass, times c squared. So the rest energy for this mass would be little f times capital M times c squared, but because it's the total energy, we have to multiply that by gamma. And for the momentum, I can say the momentum PC is equal to gamma times E naught times V over C. And this formula is coming from the beginning of this section. Maybe I don't have it here. Oh, yes, that page is conveniently missing from my textbook. Here it is. So this would be gamma times the rest energy times V over C, which is what we use there. So now I have to squeeze that in here. So gamma times the rest energy times V over C. Whoops, I'm missing a C squared. Okay, so we filled out the table, but now we have to use conservation of energy and conservation of momentum. So mc squared has to be equal to this plus this, and this plus this has to be equal to 0. So I'm going to let you try and do that on your own, but if you have questions, you can ask me in lab. And actually, we're going to be done there. So you'll have time to work on this during lab, and if you have any questions, we can discuss them during lab.